Welcome to the first of the 2019 Michelson Postdoctoral Prize lectures. The Michelson Postdoctoral Prize is an international award given annually by the Physics Department at Case Western to an outstanding postdoctoral researcher in any subfield of physics. Because of the exceptional past nominees and prize winners, it's become a leading award for early career scientists. Audrey Bienfait is the 23rd recipient of the Michelson Postdoctoral Prize. She did her doctoral work at the University of Paris-Saclay and was a postdoc at the Institute of Molecular Engineering at the University of Chicago. Audrey has performed groundbreaking experiments demonstrating the quantum limit of sensitivity in electron spin resonance and entangling superconducting qubits using phonons. She'll tell us more about this. So I'll only note how remarkable it is that she already has not just one, but 2 home runs to her credit. Also, it seems particularly appropriate that an award named after Michelson should be given to a skilled experimentalist who's developing new kinds of interferometry. So today, Audrey is going to tell us about phonons and entanglement, and I'm going to invite her to tell us about it.
Thank you for the introduction. It's well, first I want to say it's really a great pleasure to be here. I'm very happy to share my work with you. So these lectures are about making a journey through the world of hybrid quantum circuits. So I will try to flash already a little what the topics of the week are going to be. And please, if there are any questions or if I don't speak loudly enough, don't hesitate to interrupt. So let's tease you first about the topics of the week. I will talk about quantum microwave circuits, which are based on electrical circuits, so composed of capacitors and inductors that work at gigahertz frequency and that are operated at millikelvin, both to be lossless and also to go to the quantum regime. And the goal is to implement high quality factor, long-lived fields, microwave fields, and be able to control them and to manipulate them with nonlinearities. And having these 2 tools basically allow to do 2 large things. The first one is to make artificial atoms representing qubits, which allow to implement quantum information processing experiment. And the other one is because we have a very good sensitivity and a very good detection of electromagnetic field, we can build up experiment about quantum sensing. And I will try to mix and match this during the lectures and try to share all of these works during the lecture of today, the lecture of Wednesday, which is going to be about really quantum sensing with using quantum microwave to perform very sensitive magnetic resonance experiments. And the last one is also going to be about quantum sensing, which is really going to dig into how can we make a very sensitive detection of microwaves using amplifiers. But the first topic for the lectures are how can we make a phonon-mediated quantum state transfer. So that's really the topic of today. And even if now I'm in ENS Lund, the work I'm going to share with you today has mainly been done at the University of Chicago in the group of Andrew Cleland. So we can start by asking, well, what is a phonon and what can we use them for quantum devices? So a phonon, we can say that it's an elementary vibration of a medium, for example here, a longitudinal wave. And they have been harnessed in many types of quantum devices. I'm saying this with quotes. You can use them to make force sensors, very, very accurate force sensors. So for example, here you see a silicon nitride resonator, which type a single phononic mode, and which is very sensitive to any force applied on it. You can also think about cantilevers. Those are also force sensors in a sense, but you can also use them to couple, here in this picture it's NV center spin, so you couple them to the same mechanical mode because the NV centers are sensitive to strain, and so like this you can couple different entities via the phononic or the lattice that host these defects. You can also say that because phonons are elementary vibration of a medium, they can also modify the properties of the material. And so if you think about optomechanical devices, those are nanobeams that colocalize both a phononic mode and, I'm sorry, I will take that because I don't think you see what I'm pointing. So here you have a colocalization here of a mechanical mode and an optical mode. And the mechanical mode changes the optical mode frequencies. And so this allows you to have an optomechanical coupling. And so, for example, do optical to microwave frequency transduction. So that's an example of things that you can do with phonons. You can also be interested in phonons for themselves because those are a variation of microscopic objects. So there is strong fundamental interest in trying to study the quantum states of these very large objects. So that's, for example, two experiments that were done in the group of Rob Sholkoff and now at the group of Ivan Chu at ETH Zurich and in the group of Andrew Klein at the University of Chicago, where people have used simulating qubits to try to host quantum state inside phononic resonators.
So actually, just a quick question about the previous devices that you were showing, all those experiments. How quantum actually are they? I mean,
yeah, that's a very good question. So here there's absolutely no doubt that they are quantum because they are operated at very low temperature. Those are gigahertz devices. So for this, I think there's no problem of definition. It's the same for those. Those are gigahertz and operated at millikelvin temperature. So there's no question about them being operated at the quantum level when they are cooled down at this temperature. But I agree that for these two, it's actually much more challenging because, for example, here they are operated at room temperature. So that means that because these NV centers are at gigahertz frequency, you need to rely on some kind of optical reset mechanism to bring really the NV centers to be in a really quantum state. And then you have to deal with the fact that these are only like megahertz resonator, so even if you were to go to millikelvin temperature, you would not reach the quantum ground state. So no, it's very challenging to think about that, and that's at least for the low frequency devices. That's actually how do you reach the quantum ground state is one of the first steps toward making the devices quantum. Yeah.
The third one is the phonon effect localized.
Yeah, so you see, I did not explain it, but there's little defects along the nanobin, these circles, and the circles have different size. And so this changes the band gap created by the defect in the material. And because the band gap is different in the middle than in the edge, that can trap a phononic mode, a mechanical mode. So if we come back to this state, to these phononic devices, we can build quantum state on them. We can also try to untangle them. So for example, that's an experiment done by the group of Simon Groblecher at TU Delft, where they have two of these optomechanical devices, and via the optical modes, they are able to untangle the mechanical modes. So, and they can do some kind of Bell state experiment. So that's where a kind of an overview of what can you do with these quantum phononic devices. And the last point I wanted to reach was that these phonons are also waves. So you can really think of them as they are not electromagnetic waves, but you can look at what can you do with electromagnetic waves to try to see what you could do with phononic waves. And if you think about photons, well, you can use photons to carry information. So can you do the same for phononic waves? And also, I think I've heard a lot about the Michelson-Morley interferometer. And well, obviously you can use photons to make interferometers. And the question is, can you use also phonons to make interferometers experiment? And today I'm going to be mainly focusing about using phonons as carriers of information. How can we do that? And then I thought I would reserve the interferometry experiment for the colloquium, so as to spread out the suspense a little. So why would we want to use phonon to carry information? So when you think about the context of carrying information, you have to think about having two defects or two quantum systems that can host quantum states. And they're actually separated by a distance that is larger than the interaction length, so that they can't share the quantum state, they can't interact directly. And then the question is, how do you couple them? Do you couple them to a third state, a third entity that would be coupled to the two of them? Or can you use itinerant packets that would be sent from one quantum object towards the other via some kind of waveguide that you would come up with? And for at least photons, that has been very clearly answered. Yes, you can do that. For example, we can look at two experiments. The first one is one performed in TU Delft, and where two, at exactly 3 NV centers that were separated by more than 100 meters were entangled by using the optical photons that the NDV centers can generate. And on the other side, the same kind of experiment can be done with microwave photons, where, for example, here in the group of Andrew Cleland, we have shown that we could have two superconducting qubits linked by over 1 meter transmission line using microwave photons. And the trouble is that photons, you can only use them if the quantum system coupled to them. And that's actually not the case for all of them. For some of the quantum systems, you would have to maybe resort to phonons. For example, so here it's an NV center, so that's a very bad choice of picture because the NV center can generate an optical photon and so could interact with other systems via photons. But other type of spins, they do not have any possibility of emitting optical or microwave photons, but they are hosted in the material. And so because they are hosted on the material, they are actually generally very sensitive to phonons. So you can say that for some quantum system, phonons are available resources that we could exploit to couple distant systems. For example, here, 2D electron gas spins.
Sorry, question about the previous slide again. The transmission line over here, that's 1 meter long, is that superconducting or is it?
Yeah, it's a superconducting. So it's actually lossless at 90, I think 8% or something like that. Yes, so I'm sorry, I spoiled the transition. But so here we are going to try to harness a very specific type of phonon, and those are surface acoustic wave phonons. So those are waves that are trapped at the surface, and we're going to try to use them to connect to different quantum systems. So those are generally called Rayleigh waves. For each point at the surface or near the surface, when a surface acoustic wave is propagating from here left to right, the point will go through an ellipsoidal motion, and the wave has generally a linear wavefront whose size is set by the devices that are used to create these waves. And so those surface acoustic waves, they have been around for many decades and be used to create delay lines or filters for classical signals. So those are really a technology that is already very well understood and very well mastered. So we can very easily create them when using piezoelectrical materials, because when a wave is propagating, as each point is going through an ellipsoidal motion, if the material is piezoelectrical, then the motion of each dot will induce some stress in the material, and the stress will be associated with an electrical field that you can see plotted here. And if you were to put electrodes on top of the surface that match this electrical field, then a surface acoustic wave passing through the electrodes will generate microwave voltage that you'll be able to pick up. And because the device is symmetric, if you were to put a microwave generator on this interdigitated transducer, then you will be able to generate the surface acoustic wave. And this kind of interdigitated devices have this kind of cardinal sinus response, where you have a main peak of emission followed by side peaks, and something that is going to come up later in the talk is that these peaks is that there are 0 emission point. So that will be something that come up later in the talk. So another thing that can be used to manipulate these surface acoustic waves are to put what is called bright mirrors on the surface. So those are arrays of electrodes which are very thin, so only 1% of the wavelengths. And because they create mass and electrical loading for the wave, each electrode will have a small reflectivity that can build up over the array and then fully reflect the wave when there are several hundreds of these stripes. So this makes mirrors, and because we have transducer and we have mirror, we can also put up surface acoustic wave resonators, where, for example, we can have a central transducer surrounded by mirrors. And so because this mirror can trap waves that are probed by the central transducer, we can think of that as a Fabry-Perot acoustic cavities where there are several modes that we can probe. So this was a short overview about surface acoustic wave and how we can manipulate them. And so really, the goal is to use them to do this transfer of information with between two quantum systems. And there is a good interest in doing that because they have been used to couple to several other quantum systems. For example, here there was an experiment where we had two electrostatically defined quantum dots, so two spins, if you want, where the electron floating and trapped between this potential was carried from this location to this other location by surfing on a surface acoustic wave. They have also been shown to be able to drive spins just because of this strain effect on the electronic spins. And they have also been proposed to perform optical to microwave transduction. So there's really a strong interest into them from a quantum point of view. And there's also a strong interest to couple them with superconducting qubits. So all of this interest in coupling them to superconducting qubits started in 2014 in the group of Perdasing at Chalmers University, where they have shown that superconducting qubits directly patterned on top of a piezoelectric material could emit surface acoustic wave that could be detected with a receiver IDT. And then other groups build on that, and for example, were able to demonstrate the coherent coupling of a qubit to a surface acoustic wave, and later on be able to create arbitrary quantum state inside one of these modes of these acoustic Fabry-Perot cavities. And here, really, the goal is to have two superconducting qubits that are very far apart and that will be connected with this itinerant surface acoustic wave packets. So that's really the goal. Oops, sorry. And there are two things we need to be able to overcome to be able to do that. The first one is that we need to be able to release and cache these wave packets that carry the information. And it has been shown that in theory, to be able to transfer efficiently this quanta and not lose quantum information on the way, it's better to be able to modulate the rate so as to emit and receive a symmetric wave packet. So the symmetry of the wave packet is not strictly necessary. You could do without it, but I'm going to focus on that for this talk. And the way to understand this requirement is if you have so a qubit, two-level system, we'll say, that is just suddenly coupled to its environment. It will then relax from an excited state to its ground state by releasing a photon or a phonon. So here it will be a phonon. And the shape of the wave packet will be an exponential decay. Now, if you were to want to reabsorb this wave packet, because the quantum state served by the qubit is now in this wave packet, you don't want to lose any of it. So if you want to reabsorb it, the trouble is that you see now that it's coming back towards you again, you have an infinitely sharp wavefront coming at the qubit. And the qubit is like any kind of physical system. It has a finite line width, so that you can actually only capture at a finite rate. And so this means that you can only capture part of the wave packet. And if you go through the series, and percentage of 54% of coupling will happen at best if you don't modulate the coupling. So the solution that theorists have come up with to solve this issue is to actually modulate the coupling when the qubit is emitting its information, so that actually what is emitted is a symmetric wave packet, and then there's not this problem of infinitely sharp wavefront, and there is no problem for the information to be reabsorbed again. So that's the first hurdle to overcome. If we want to have an efficient transfer of information between one simulating qubit and the other, we need to be able to shape the wave packets. And then the second one is that, so that's something that's already been realized in many microwave realization of quantum states transfer by groups in the last, I think, 2 years, we'll say. And so the second hurdle to realize is that now that we have this simulating qubit coupled to this phononic channel, if we were to realize the experiment exactly like it's captured on this slide, there will be a slight problem, because there is absolutely nothing preventing the simulating qubit from emitting both left and right. And if you're emitting both left and right, then it's not possible to fully transmit the information from one simulating qubit to the other. Yeah. So the way that we figured we would circumvent that problem in our experiment is to use this kind of Fabry-Perot resonator. So we deposited aluminum and lithium niobate, which is one of the most piezoelectric substrates. And at the center here, you can see interdigitated transducer. So we can use this transducer to generate phononic waves that can propagate left and right. And on each side of this transducer, at a distance of 1 millimeter away from the transducer, we have placed Bragg mirrors. So those Bragg mirrors are able to reflect any phonon emitted by the transducer, and then they will propagate backwards towards the IDT and be able to be reabsorbed by it. So the travel time for a wave packet is approximately of 500 nanoseconds through the resonator. And now if we are to place two simulating qubits on each side of the central transducer, then each of them could be able to emit surface acoustic wave that would propagate through the channel, come back towards the transducer to be recaptured by the simulating qubit. So that's basically the plan of the experiment. Right now I've been very vague about what is a simulating qubit, and now I'm going to take the time to explain it.
And also how you tune the coupling.
Yes, exactly. So that's the big picture, and we can move to smaller. So this artificial two-level system is implemented by this LC oscillator. So right now we are going to focus on the blue part. So it's a capacitor in parallel with a squid. So a squid, it's a two Josephson junction put in parallel. And right now this Josephson junction, you can just take them as inductors. So this can make a LC oscillator. And because these Josephson junctions are actually highly nonlinear elements, when you actually derive the potential for this electrical circuit, as you will do for a mechanical resonator, then you find that the potential is actually nonlinear. And so if you solve for the energy level of the system, you will see that the energy level are actually non-evenly spaced, so that you can address the transition between level separately. So basically, right now in this talk, we're just going to focus on the first two states that we call ground and excited state. So this is what it actually looks like in reality. Here you can see the capacitor, which is a big pad that is capacitively connected to ground, and it has this cross kind of shape to be able to connect to different lines that we can slowly dig into what they are. The little square here contains the two Josephson junction, so they're much, much smaller than the capacitor. So the first line connected to the qubit is focused on how do we read these artificial spins. Well, it's done via a readout resonator that is capacitively connected to the qubit, and here actually is inductively connected to some readout lines. We send some microwave tones that reflects on the resonator, and we can monitor its amplitude and its phase. So if we plot on some plane for the quadrature of the signal, that's to say the in-phase quadrature and the out-of-phase quadrature of the transmitted signal, we can plot for each time that we repeat the experiment what is the average point in this plane. And when the qubit is in the ground state, we see that they are mainly localized on one spot of the microwave plane. And when we repeat the experiment, when the qubit is in the excited state, we see that they are localized in a different spot. And we can then, by just dividing this plane in two parts, I can determine whether the qubit is in the excited or in its ground state. And from this, we can just infer, I'm sorry, I did it again, hi. We can just infer what is the probability of the qubit to be in its ground and in the excited state for each experiment.
Is the error due to non-ideal preparation or measurement, or is that just is that intentional?
So in this case, I think we actually don't capture this graph very often, so that's the best one I could find. But you are right that there are two kinds of errors. There's how do you first prepare in the excited state that could have some error and say that, well, maybe you just left in G. And then there's the error that you commit when you are measuring. And these errors come from the fact that when you are sending this microwave tone, you are also populating the resonator with photons. And these photons can also come and populate the resonator, so that's one error. You can also think that if the qubit started in its excited state, it generally takes some time to measure it. So from, let's say, 200 nanoseconds for the most efficient experiment to maybe a few microseconds. And during this time, it's possible for the qubit to go from the excited state down to the ground state. And that also would count as a false positive. So there are many reasons why we do not reach 100% determination. And here, the best number that we get is maybe 94% of readout fidelity, we'll say. Yeah. So then the question is, yes, how do we prepare in the excited state? And for that, we use this control line that allows us to send drive pulses at the qubit. And if you plot the qubit on the Bloch sphere, where you have the ground state at the bottom of the sphere and the excited state at the bottom, sending this microwave tone at the electrical qubit will allow you to drive the quantum state around the Bloch sphere, around an axis that is contained in the equator. So basically, you can reach any point of the Bloch sphere by this microwave rotation. So in particular, if you start from the ground state, you just need to apply a pi pulse rotation to go to the excited state. And the pi over 2 rotation will take you to a superposition of state between ground and excited state. We can also change the frequency of the qubit. And this is because instead of using just a single Josephson junction, we have used two Josephson junctions in parallel. So this traps some flux. And by applying some current pulse through this squid, we can modulate this flux and modulate the value of the inductance of this squid, and then change the frequency of the qubit. So here we can actually tune it over several hundred of megahertz. And so that concludes the part about how we can implement experimenting qubits and control it. And then now the big question is how can we couple it to surface acoustic wave and implement this kind of modulation of the wave packet shape. And so for this, we, I'm sorry, I actually add more on simulating qubits. So there are two important times for simulating qubits. The first one is, well, once you're in the excited state, for how long can you stay in the excited state? Because you will inevitably go back to the ground state. So that's called energy relaxation time T1. And we measure it by applying this pi pulse, and then waiting for a time t and measuring what is the decay. And a typical number for distributing qubits is about 20 microseconds. And the field is mostly right now ranging from 10 to 100 of microseconds of T1s. And obviously, it's like everyone, we always want longer time. So there is a strong effort to go beyond 100 microseconds. The second important state is if you prepare if you prepare a superposition state, how long can this superposition state maintain its phase? And so that's called phase coherence, so T2 time. And for this, what we do is we first prepare the superposition time, wait for a time t, and then go back to the measurement axis, which is the z-axis, to determine how long we have kept this phase. And so we can see an exponential decay of approximately 2 microseconds, and we have put extra oscillation by controlling the phase of the pi/2 to make the fitting of this exponential decay easier. And here we reach a T2 of 2 microseconds, which is right now by the standard of the field quite low, because more typical number are around 10 to 50 microseconds of T2. Yes.
By the standard of this field, you mean with superconducting qubits?
In the field of simulating qubits. So there are many different kinds of systems. Simulating qubits are thought to be more scalable for quantum computing because they are more easy to engineer, but they do not have the best coherence time, for example, compared to other systems such as ions or atom, or for example, NV center, which are much more uncoupled from the environment than simulating qubits. And then that's the trade-off. If you're more isolated, then you get longer coherence time. But if you have more coupling, then it's easier to engineer and control the state. But then the trade-off is that, well, you're more coupled, so you have more noise and you have less good coherence time. Yeah. And so now we come to the point where we have this simulating qubits that has this quantum state that we want to transfer to phonons, and that we have to couple to this transducer to be able to emit these phonons. And we do that via an inductive coupler. So this is just a network of inductances. You see two grounding inductances through which flow two currents. So the current on the right branch is the one that is going to also flow through the transducer by a mutual inductive coupling. And actually what we want is to control the amount of current that is going from the qubit to the IDT. So for that, we just play on the value of an extra inductance that is bridging the two grounding inductances. And by controlling the value of the inductance, we can either shut off any kind of current flowing through this branch, and so isolate the superconducting qubits, or we can maximize the current flowing through the right branch, and so maximize the amount of energy going from the qubit to the IDT, and so maximizing the emission of phonon by the IDT. So this modulation of the inductance is done by also a Josephson junction, because if we control the phase across the Josephson junction by DC current flowing through this wire, then we can modulate the effective inductance that is implemented by the Josephson junction. And so that's actually what is done via this wire here. It's some modulation of the DC current flowing through the two grounding inductances that are there and there, and that is flowing through the Josephson junction, which is right there at the middle of the two inductances.
So at the end, you just have to modulate the current, and that modulates the coupling.
Exactly, it's a DC control of the coupling. Yes.
So that the Josephson junction is at that angle there?
Yes. Yes.
Why is it? It looks like it's shaped like two little arrow things.
So this picture is taken before the Jefferson junction deposition, so there's actually a black spot where it's supposed to be. But it's really connecting two arms that are sitting at 90 degrees.
Right.
Yeah. You have to imagine this, well, it's too far away, but yeah. So now we have our two devices. We have the superconducting qubits and the coupler. To have the good T1 and T2, I've shown you we had to fabricate them on sapphire, which is a non-piezoelectric material. And then we have the lithium niobate chip, where we have been able to make a Fabry-Perot resonator that can contain this phononic wave packet that we want to emit. And then the question is, well, how do we couple them together, these two chips? And we do that by a non-galvanic assembly, where we actually put 5 micron thick resist pillar on the white area that you see. And this area also contains alignment crosses. So we can just use a mask aligner to have these two chips coming one over the other and align the crosses from one chip onto the other. So this brings close the two inductors that are sitting on each chip to perform the coupling between the coupler and the IDT. So if I go back, this is actually this part which is done by these overlaid inductors. The typical size of that is approximately 10 micron thick for the wire and 5 micron separation between the two chips. So once we have assembled everything, then we can place everything inside the cryostat, cool down to 10 milli-K, and perform the experiments.
So your inductor is just a pair of wires, like a strip line and a chip?
Yes, those are just strip lines, yes. So the first question that we can try to solve once we have bring up the qubit, measure the coherence time, figure out what are the frequencies, are we really able to emit phonons? So for that, we want to look at whether the qubit loses energy by this emission of phonons. So we are going to do T1, this T1 measurement. So we apply a pulse to go to the excited state, then wait a time T, and measure how much the qubit has lost from its energy. And we repeat that for different time T, and we also sweep the qubit frequency. So when we perform the experiment, that's what it looks like. And we see, if we look at very short time, that so the color is how much excitation is in the qubit. Red means that it's fully excited, so that's what we start at time t equals 0. And when the qubit has lost its excitation, then we go towards the blues. And we can see that for 2 times, then there are an relaxation that is very slow, whereas at the middle, around 4 gigahertz, we see a very sharp relaxation. And if we extract the relaxation rate, we find that we have indeed these two non-zero emission points and the main emission point. And so that really looks like the shape of the response of the IDT. So that's already one thing that we can say, that if we are here, then the qubit relax by emission of phonons. So I've got to point out that this emission of phonon is actually very fast. It's a few nanoseconds. So that's basically nothing comparable with the usual T1 time of the qubits, which was more of the order of microsecond. And then if we look at what is happening in the middle, we see that once we have emitting the phonon, waited for approximately 500 nanoseconds, then we see that the qubit state the qubit is actually re-excited before losing its excitation again, and then another 500 nanoseconds, then the qubit becomes excited again and lose this excitation. And so what's happening is that the qubit has released a phonon by the transducer. The phonons are propagating through the resonator. They bounce on the mirror, and then they come and re-excite the transducer and re-excite the qubit. So this revival of excitation really indicates what is the mirror bandwidth. So in this range of frequency, we can have phonons and we can see the phonon coming back.
Is this like a kind of Rabi oscillation or a sort of quantum Rabi oscillation?
Um,
Where you're sort of emitting and absorbing the same phonon?
Well, if it was a standing wave phonon mode, then I would say yes, because you are just emitting into the standing wave modes and then it's going back.
Yeah.
Here it's an itinerant mode, so you're emitting a phonon, it's traveling.
But you've got the mirrors, so does that make it more like a standing wave mode? Or?
Let me come to that in a second, in a few slides, so then the discussion is going to be clearer. And then the last element that we need to try to make this efficient transfer of phonons is to be able to control the coupling to the transducer, so to control, in a sense, the coupling rate. And so we can look at that by playing on the current flowing through the tuning branch of the radiation junction. And if we do that, we can see that if we take the T1 time at this arrow point, we see that the T1 goes from 10 nanoseconds up towards the increasing time of a few microseconds. So we see that we can tune the relaxation rate by over 3 orders of magnitude. And basically, we can distinguish two regimes. The first one is when we are the T1 time that is much smaller than the round-trip time, and one where the T1 time is much larger than the round-trip time. So this kind of make up two kind of situation. When the coupling, the excitation time is very much smaller than the round-trip time, then you can really think of the phonon as an itinerant wave packet that is stored in the SAW resonator. It's emitted by the phonon, going through the channel, and then coming back and re-exciting several times the qubit. Now, in the other kind of situation, where the phonon, where the T1 time is much longer than the round-trip time, you have the wave packet of the phonon that is propagating through the resonator, but it's coming back to the qubit before the qubit has really emitted everything that is stored inside. So when it goes back, at time like 500 nanoseconds, an interference is happening between what is still stored in the qubit and what is actually coming back from the round trip within the resonator. And depending on the phase that is accumulated by the phonon, the wave packet that has traveled through the resonator, then this interference can be constructive or destructive. So in a sense, that's in the time domain. We can look at also what happens in the frequency domain. So if we go to the frequency domain, then we have all of these Fabry-Perot modes that are trapped inside this very big surface acoustic wave resonator. And now because the T1 time of the qubit is very large, that means that the line width of the qubit can be quite small. So that means that if we are to do some kind of Fourier spectroscopy of the qubit and sweeping the qubit frequency, then we will be able to see each of these individual modes. And that's actually what we see. When we do the qubit spectroscopy, what we see is all of this avoided level crossing. So in the case where we have a very long T1, then we can say we have this kind of Rabi oscillation, and they are just all smashed together.
So it means how do you get the tau? Because you have to...
So it's just given by the velocity of the surface acoustic waves. They're actually very slow, maybe 4 orders of magnitude less than the light. And because the mirrors are separated by 2 millimeters, when you emit them at the center, it just takes them 500 nanoseconds to go back to the transducer. And then on the other side of the picture, we can do the same thing. When the T1 time is very short, then the qubit line width is very broad, and then we address several of these Fabry-Perot modes. And so that's why when we go into the time domain, we can say that we have very sharp, well-defined time domain wave packet. So that's really the full picture of why we can use a SAW resonator to exchange itinerant excitation between the superconducting qubits. And that's now the time to try to really do an efficient transfer from one qubit to the other. So I've explained you that we need to do this shaping to hope to have an efficient capture. And so that's what we do by playing on the tunable coupler so as to engineer the relaxation rate of the superconducting qubit. So that's what you see here. Instead of the previous exponential decay, we see that we now have some kind of hyperbolic tangent relaxation that allows us to really have this smooth, symmetric phonon wave packet propagating through the resonator. And when we do really the time-reversed operation of the emission when we capture the qubit, then we can see the qubit be relaxated. And we find that we have a 67% efficiency of capture for this surface acoustic wave phonon. We can prepare different kind of quantum state just to check that it does not work for a single one. So we repeated the experiment and did that with the ground state, the excited state, and then the superposition state, E plus G. And we find that we are able to transfer them too. And when we try to make a tomography of the process, that's to find exactly what operation you need to apply to the Bloch sphere at the input to get the output Bloch sphere, we find that we mainly have a process that looks like identity, meaning that transferring the phonon, the quantum state via the phonon, doesn't really change the quantum state. And then I promised you 100% efficiency. I only have 67%, so we can try to determine to see why is that. So what we did is that we tried to capture successive transit of the phonon. So the submitting qubit is emitting this phonon inside the resonator. The phonon are both impact once, and then we actually do not capture the first transit, but let it evolve a second time, and then look at its captures, and then do that several times. And we can see that every time that we go and try to capture a different transit, then we have an exponential decay of the capture efficiency. And that actually means that the main mechanism responsible for the losses are acoustic losses within the surface acoustic wave resonator. And we find that this kind of decay, this 67% decay, when we convert it in time, it agrees with the surface acoustic wave quality factor. So right now, that's a kind of a big interrogation in our experiment is what are those exactly these acoustic losses? Where do they come from? How can we make our system better? So that's one thing that we're considering.
Is it basically leaking out of the mirrors? Is that what you're saying? Or
I'm sorry?
it's just leaking out of the mirrors, the wave? Is that what's happening?
So there could be many kind of different acoustic mechanisms that would make losses happen. The first one that you can think of is that the surface acoustic wave generally they are on a track. But if you place the mirror too far away, then the wave is going to diffract, and you're actually only going to reflect part of the wave. So that's already one explanation. The other is that, well, once you have left the transducer, you are basically propagating through free space until you the wave reflects on the mirror. And because you reflect on the mirror, the velocity is different. So you can see that you are kind of changing the properties of the material. So it kind of makes some kind of acoustic impedance mismatch. And so that could induce some scattering into other acoustic modes and be also, from the point of view of the qubit, be seen as acoustic losses. And actually, we think that this is the main mechanism, but it's very difficult to prove. So we haven't been able to really check that this is the case, and if yes, how to solve it. Yeah. Then once we are, so that's complete the being able to emit one phonon and be able to capture it again. But 500 nanoseconds, at our scale, it's a very, very long time. It's long enough that we can put different quanta inside this phononic channel. So we can have the qubit one excite, lose its excitation, so have a first phonon traveling the resonator. Then we can have the second qubit, which we can also connect to the surface acoustic wave resonator and have it lose also its excitation, half a round trip after the first qubit. And then because we have these two phonons that are traveling the surface acoustic wave resonator, they don't have a label anymore except the time of emission. So we can have whichever qubits we want, pick them up. So here, we chose to exchange the quantum state of both qubits so that actually qubit 2 would capture the phonon emitted by qubit 1, and qubit 1 would pick up the phonon emitted by qubit 2. So like this, we have two qubits that at both a quantum state have it emit it to the surface acoustic wave channel, and then as soon as they were transferred in the shape of phonons, we were able to swap the quantum state using the channel. So when we try to look at how good is this process, well, we are limited by this, once again, these acoustic losses, and we find that we can make this double swap happen with a fidelity of 64%, which is, in the scale of quantum processing experiment, not very good, but it's more of a proof of concept that this can happen. And the last thing that I wanted to show you is that we can also create entanglement over the channel. So this means that we want to have a Bell state that is, that's to say, a state where one excitation is shared over the qubit, and we want to create this entanglement, this sharing of excitation, by having a transfer of energy via the phonon. So what we do is that we prepare qubit 1 in its excited state. This time we modulate the rate precisely so that qubit 1 only loses half of its energy. So half of its energy is still within the electrical circuit, and half of it is propagating through the surface acoustic wave channel. And then we have the second qubit, after the round-trip time has elapsed, pick up this phonon. So right now, at the end of this sequence, then the energy is half in qubit 1 and half in qubit 2, thus creating a Bell state. So that should be the ideal Bell state with a 1/square root over the two probable states, qubit 1 being excited, qubit 2 being disexcited, and vice versa. And when we do the tomography of this state, we actually find that, because of losses, it's very probable for qubit 1 to not have lost this excitation and qubit 2 to not have recovered the half excitation stored in the phononic channel. So we find that basically we have a Bell state with an 86% probability. And so that concludes what I wanted to show you. With this, we are able to create entanglement between the qubits using phonons. We are able to transfer quantum state using this phonon between one superconducting qubit and the other. So this is really the beginning of a journey, because what I've shown you is really confined to a surface acoustic wave resonator. And so we actually have only the same emission point. This is also limited by acoustic losses. We have only 67% transfer efficiency. And really the goal of this experiment is to develop unidirectional transducer so as to be able to emit at different points. We also want to really investigate what are these acoustic losses and how can we make this experiment better. And then once we have solved this very large issue, then we can try to think of making a larger test of acoustic entanglement. Can we do a Bell inequality test using these traveling phonons? And once we have this traveling phonon, then really the idea is to go towards quantum optic experiments, the first one being realizing an interferometer. But so we already started doing that, so please come on Thursday, I think it's the colloquium, to see the results. And I want to thank, of course, the whole Clement group, which many people participated in making this experiment happen. And also thank you very much for coming on President Day and listening to the talk.
So I guess we have time for some quick questions. Okay, go ahead.
Is there any advantage of using phonons instead of photons as the mediator?
I think there is an advantage when you can couple two photons. So for example, if you take 2D electronic electrostatically defined quantum dots, then there's no obvious way of generating a photon with that, an optical photon or a microwave photon. But it's very easy to generate a phonon. So I would say if you can't go towards photons, then phonon may be an option. So coupling quantum state is one way that you can look at this experiment, but I also like to say that we can also use the quantum systems to really probe the phonon. So you see it's a two-part exchange.
So when the qubit emits a phonon, the quantum state is transferred to the phonon, and I can see how like the amplitude of the acoustic wave would encode the amount of 0 or 1 or E or G. But I would think that I'm trying to figure out where the phase information is stored in the phonon, which I would naturally think would be the phase. But then it seems that since it's itinerant, it travels and comes back, the phase would depend on the path length.
That's very true, but here you have the qubits and the traveling phonons that are exactly at the same frequency. So we actually spend a lot of time making sure that throughout the sequence they have all the same frequency. So you can really think of them as evolving on the same time scale. So even if the phonon is propagating, it's acquiring the same kind of phase, and the photon, the qubit state is picking up. So if we make sure the frequency are the same, then there's no phase problem.
So before we go to the next question, I just wanted to mention that the next seminar in the series is Wednesday, same time, same place. And there's also a reception on Wednesday at 4 o'clock. So you're all invited to that. And what?
So you mentioned in the beginning that possibly one could do similar things with NV centers. And I don't know enough about Josephson Johnson, so I'll ask my question about NV centers, but maybe there's an analog. So in an NV center, you have an excited state, and now you wanted to give its energy to a phonon that's being emitted. How do you control whether it loses its energy to a photon, which is sort of the natural experiment that Jesse would be doing, versus giving it to a phonon? Where does the electron-phonon coupling come in or something? If you have some kind of electronic state that is your qubit, how do you control that it goes to the phonons?
Right. So really, I think you have to start from the Hamiltonian of the defects to see where is it possible for strain or stress to come into play. So how does stress modulate the energy level of the NV centers? And from this, you will be able to see whether it's possible to couple two phonons to this kind of stress displacement wave compared to being able to emit an optical or a microwave photon. So I really think this starts from the defect Hamiltonian. And for spins, I think it's going to be very hard to be able to emit, for electronic spins such as NV centers, to be able to really emit phonons, because I think the coupling is very, very tiny, just because the NV center is such a tiny entity compared to the surface acoustic wave, which is more on the micrometer wavelength scale.
So is there a similar problem for your Josephson Johnson qubits?
No, for
they lose their energy in another way, then how,
well, then yes, it's how do you couple to what modes do you couple to? That basically is the question. And it's true that if you want to emit phonons specifically, then you have to engineer the coupling to the phononic mode so that it's dominant over all other coupling mechanism. So here, that's what we did with this tunable coupler and this transducer that are coupled by this override inductor. We made sure that the main path of emission for the qubit was by emitting phonon. If the best emission rate that we could get was maybe 10 microseconds, and the intrinsic lifetime of the qubit is 20 microseconds, then we would only emit 50% of the energy through the phonon. So we would not be able to do this kind of experiments. Yeah.
Yeah, well, I guess in light of the time, I'll let Shule ask one quick question.
So you mentioned something about the unidirectional transducer. Is this something about related with like a chiral phonon? You have, breaking inversion symmetry, so propagating one with the other direction, have different dispersion.
That's one way that you can do it. Yes, that's true. Having different kind of propagation low in different direction. What you can also do is emit waves in both directions, but waves that interfere differently. So you can have some kind of a special transducer where you have actually two kind of emission pattern. And actually each emission pattern is going to emit a wave on each side of the IDT. And because of the way the emission patterns, the patterns are made, the waves have different phase on one side and the other. And so basically the answer is that one side will interfere destructively, the other side will interfere constructively, and so you will have emission only on one side. That basically the idea that has been developed for directional transducer, yes.
So I do see there are other questions, but in view of the time, maybe we'll save them for private discussion. Audrey is in ROC 203, which is Brian Lynn's office. And as you said, it's a journey and we're looking forward to the next step.